right? So today we're going to talk about large language models, and we're going to start off with answering that question. What the hell is a large language model? Where does it come from? So of course, let's start with history. It started with something that has to do with functional programming, right? Some of you, especially the old chaps like me, will remember, yeah, there was this little chat program, this kind of computational therapist called Eliza in the 1960s. It was written in Lisp. And what it did was to cleverly combine questions and the rule engine about answering questions in a fake therapy session. It was quite effective, very small, right? And it did fake for a while a real therapist, right? So that's where the basic idea comes from. And then, machine learning evolved, and then people were thinking about how to actually create artificial intelligence. And the best way to do that is to replicate something that we know, basically our own brains. So the idea of neural networks was conceptualized and then implemented in the 1990s, and have been an integral part of machine learning ever since. At some point, the evolution continued, and people came up with the idea of if we want to treat let's say, effectively treat text and language, we should basically treat sentences as vectors and do matrix multiplication on vectors. So Word2Vec was one of the first frameworks in that space to do exactly that. At some point, people said, okay, using tokenized vectors is a good thing, but we sort of need to teach our neural networks the ability to understand some context, right? And they came up with LSTM, which stands for long short-term memory. It's a kind of strange name, but what it actually means is the ability of that model to keep segments in context and to analyze this and recombine them to answer specific questions. And that allowed the language models back then to actually do summarization. So you give a long-form text into that model, and it could basically create a summary, and also classification work, which was quite useful in natural language processing. And that, again, led to another group of folks saying, OK, this is great stuff, but we need to do something really proper. And everybody remembers like the first translators, putting a sentence in French and translating it back to English. It was always chunky. And Google, having invested a lot of time in trying to create something that really worked, came up with the Transformers concept, right? And that was a result of a lot of research on how to effectively do translations in languages that have a completely different syntax and different grammar, right? Like if anyone wants to learn a foreign language, an Asian language, right, they will absolutely know how difficult it is because the syntax in Asian languages is vastly different from, let's say, Western languages. And even within Western languages, sentences sound strange when you're speaking. You take an English sentence and translate it word for word into French. So that ability to create a model that's capable of actually creating and composing a sentence that makes sense even to a native speaker, that required a different approach. And that was the transformer model, which basically used a concept called attention. And attention is at the core of everything, because it says the model should be able to take a sentence and discern between the relevant and non-relevant parts. So the fill words and the actual context, right? And focus on that and keep that in memory. So the LSTM stuff is actually also quite relevant to transformers. And essentially build a model and self-learn using these principles to create something that actually has a proper results, right? So transformers are based on two principles, having an encoder that basically reads a sequence and decodes it by predicting the most likely next token, right? And the way it learns is to say, okay, if I take a partial sentence, right, and I mask parts of the sentence, I'm going to try to predict what words should actually fill in those masks, or should go into those masks. And if I'm right, when I compare it with the actual sentence, that improves my model. And that also allows transformer-based models to do something that's actually really clever, and that's actually self-learning, right? So essentially, when you train such a model, you take sentences, the model masks bits of the sentence, predicts what would actually come into those gaps, would fill in those gaps, and then compare it with the result. And when it's good, it basically takes that and learns even more. So that being said, how do you actually get from that kind of model to the OpenAI's ChatGPTs of today, or the large, the text, the ability to translate text from Chinese to English without that sounding strange? Well, it actually requires a lot of data, right? Enormous amounts of data, because this model has to learn from scratch everything that it needs to know to be able to actually perform those clever tasks. So there's another aspect that's actually quite important in transformer architecture, and that is the ability to process sequences in parallel, which is also the reason why everybody's so crazy about GPUs, right? Because GPUs allow that parallel processing, and basically the scale of the learning requirements that these models need. And not only does it need that, it also needs a lot of data to do that. That's why we also talk about large language models as opposed to the smaller models in traditional machine learning, because we actually feed them really, really humongous amounts of data in their data sets. So just to give a few examples, there's Common Crawl, which is a collection of 50 billion web pages from the public internet. That's used in large language model for training. Wikipedia, kind of obvious, right? And for instance, especially for those large language models that are really good at providing code assistance, like in GitHub Copilot, they use a combination of public repositories from Jupyter and GitHub. So that being said, well, when we just look at that concept, we obviously want to know what are the common implementations of large language models. Well, obviously, Google Translate has some form of large language model. It's not exactly a large language model because they basically evolved the transformer pattern to, as they move forward in time, but it is very similar, and it gives them the ability to translate any language pair, right, regardless of the syntax. Obviously, the elephant in the room, OpenAPI. I mean, awareness of large language model exploded this year when people started using whole-scale ChatGPT and saying, oh, wow, this is insane. Why? This is so good, right? What does it do? I can generate poems and all of that. That's crazy. And that's specifically because GPT is one of the large language models. And not only do we have ChatGPT, we also have a lot of different other large language models that are published by different organizations. For instance, Facebook's Meta has its own model. Microsoft has its own models. There are different research organizations and startups that are focused on creating general purpose large language models for public use or research use in academia. So again, to reiterate, what are the actual ingredients for a large language model? So first of all, you have to pre-train it on large data sets. And that's where that becomes a bit difficult, because yes, you can take Common Crawl, right? But to be honest, Common Crawl also contains enormous amounts of gibberish, right? It's the public internet after all, right? So you can take Common Crawl, but you need to refine it. So it takes a lot of resources to refine Common Crawl, remove duplication, remove the gibberish, and create a refined data set, right? But in addition, what's also quite important is to have access to large quantities of digitized books, right? So a lot of these organizations license content from libraries, right? And from other sources to train their models, because the more text you've got, the better the model. And that also introduces an unfair bias, because the reason large language models are really good in English specifically is because 60% of the internet is English, right? And it's not as bad for the other mainstream languages like Spanish or French or German, because there's also sufficient amounts of data to train the language models on. But other languages have a significant smaller data set to train on, and that's why the language models in those languages become more difficult to do. In fact, this is such a significant problem that the Indian and Chinese governments are spending lots of money in providing curated translation of English text into Mandarin and Hindu to make sure that they have enough content to train specific language models in those languages. And on top of the data set, and that also requires validation and filtering of the data set, you also need to make sure that the data set you train your language model on does not contain any private data, so PII, right? So personal data has to be removed. So it takes, again, a lot of resources to make sure that that's not in there. You don't leak sensitive information, like bomb building manuals, anyone, or anything of the sort. All of that has to be removed from the model. You can't just take off-the-shelf stuff and train your model on it. And then, again, there's another aspect that plays a role. Some of you might have heard, yeah, let's say ChatGPT has been trained on 80 billion or 200 billion parameters, whatever that means, right? And this model has 70 billion or 1 billion or 8 billion parameters. And you tend to think, okay, what does that mean? Basically, obviously, it's an indication of the amount of data that was used to train the model. But that does not necessarily mean that bigger is always better. Right? Because if you have a huge model with a huge data set, it also means that it takes a long time, it takes a lot of resources to run it, right? Because the model is big, right? It has to load itself in memory. You need GPU memory. That's also costly. So generally, there's always that consideration that sometimes a smaller model with less parameters, less baked-in knowledge, right, to cleverly answer questions or write poems or whatever, might also be a better idea because there's a performance trade-off to that. So that being said, another technique, when you take a specific, like a general purpose language model, you can actually also do something that doesn't require training a model from scratch, right? You take a foundation model, right, a pre-baked one, and you say, I'm going to fine-tune it. And fine-tuning is basically taking exactly that model and saying, I've got this set of data that I want to add onto the model, right? And do a post-training or fine-tuning of an existing model with additional data to add weights or to basically make it turn it into an expert in a specific domain. So this is a good technique to make sure that you create a large language model that has a specific domain knowledge. And usually what you do is to take a smaller model and then fine-tune it with a specific domain. And that obviously also improves the performance. So you can have specific models for, let's say, an expertise, an area. For one example would be to say, I'm going to train a coding large language model for a specific language, like Scala, for instance. And actually, that would be a good thing because there is very little Scala support in large language models. If anyone has tried to do a conversational coding session with ChatGPT, the results are rather poor. So that being said, when you have a model, you need to interact with it, right? And essentially, it comes in two flavors. The first one is known to most of us, chatting, right? Having a conversation. So, yeah, I'd like to have a poem, or do you know when to shave an alpaca, whatever you want to do. You can have a conversation with a large language model. That's kind of nice as a gimmick, and certainly if you're basically using a large language model in customer support, that's probably the way to go. The more interesting one for us, because after all, this talk is about how to use large language model in enterprise context, right, and integrate that with applications, it's the actually instruct mode. And instruct is essentially the interaction with a large language model asking the model to do something. Like, for instance, summarize this text, please, right? So a thing that some of you might know from, let's say, video conferencing software is we just say create a transcript, and then you ask a large language model to do a summarization of the transcript of the video chat, for instance, or classification, or evaluation, etc. So instruction is actually a very useful thing. And the way to interact with a large language model, quelle surprise, It is using a prompt. So many of you heard the word prompt engineering. Sounds a bit weird, especially if you're a software developer, because when we think about software development, say, okay, I'm going to write some code, right? But no, prompt engineering is actually talking to a large language model and telling it what to do, right? It's not very engineering. Doesn't feel doesn't feel like much engineering, but it is specifically because you instruct in your natural language, you instruct the large language model to do something. Like in this example, we're just telling it to, create a made-up list of books and do the output in JSON. And you just tell it, here, JSON output, and you get it. So essentially, you ask a question, provide some instructions, and you parse the response. That means that if you accept that strange concept, which is not very much software engineering, right? You can actually interact with a large language model as a service, because you have an HTTP interface, you basically prompt, and you get a response, and you can incorporate the result in your application. So again, coming back to the typical tasks, classification, summarization, entity extraction. That's the stuff they're really, really good at. And interestingly enough, that's the stuff that we're generally bad at without machine learning or without large language models, because anyone, especially the entity extraction bit, is a pain in the neck, right? If you're trying to parse a PDF, right, or some kind of unstructured document, and you want to get the address, and you have to write a parser, a combinator, another parser, et cetera, that's like really, really tedious. And that good thing about large language models is that they're actually quite good at it, because you can say, this is what I want. I want you to get the address out of this document and put it in a structured format, JSON or whatever. They're really good at that. Summarization is as well. That's the core task of generative large language models, is to say, okay, this is the text, now summarize it, please. And classification. So if you say, I'd like to know what topics are discussed in this piece of text, or you have a specific categories, and that's specifically important in industries where we have a lot of let's say, human-machine interaction, right? So doctors, healthcare, legal professions, et cetera, where documents are parsed and need to be classified and sorted, and where, until now, we had to rely on human labor specifically to do that, or we can automate a lot of these boring tasks by using classification features in large language models. So, all that being said, now we know a large language model is something that you can deploy somewhere and you can interact with using a prompt, right? Prompt engineering. We'd like to know how to actually really use them. Because for most of us, it's like, okay, there's ChatGPT, but how can I actually use a large language model and build that into my application? Well, it isn't that difficult, actually, but specifically in the last couple of months, a lot has happened, right? So there are 3 different types of deployments that we think of. The first one is using an inference API. That's like the simplest thing, right? When you have in fact, when you have an OpenAI account, you can just, you buy some credits and you can actually interact with GPT and their APIs. Very simple. It's hosted, and the pricing is more the issue because it's actually kind of expensive, but it's the simplest type of integration. The second bit, or the second option, is to use a hosted model as a service. So all cloud providers do that. In addition to AWS and Azure, there's also a company called Huggingface that some of you might have heard. They're specialized in also providing models as a service. And you can essentially say, I'd like to run this model, right? And you run the hardware for me, and I can interact with that, and I can integrate my large language model into my application using that hosted model as a service. So Sagemaker is an option in AWS. You have Azure ML that does that, et cetera. And lastly, if you're, for various reasons, you're very privacy conscious or you have specific regulatory requirements, you can also host your large language model in a container with specific GPU instances, which are a requirement to run them in a Kubernetes cluster, either on-prem or in your cloud environment. Oops, okay. And if we look at model as a service, there are a few things. The first one is giving a shout out at Huggingface. It's a company, it's a relatively recent company focused on providing support and a community for machine learning in general and large language models in specific. And it's a bit of a combination of a GitHub for ML, so it's really a source of like, you can find large language models, you can find resources and frameworks, etc. And most specifically, they provide a Python library that facilitate pulling large language models called Huggingface Transformers. It's very easy to use, so that makes it very easy to interact with and also overcome the obstacles of running this stuff, because obviously the whole space is so new that the grade of the innovation was quite quick. And they also provide runtime environments for large language models. AWS has Sagemaker, which is like the go-to tool for everything that has to do with machine learning, and specifically AWS expanded their offering to also allow running large language models as a service. Azure and GCP followed suit with their own environments. All of them have bindings to Hugging Face, so generally saying, I'm using my large language model deployed in AWS, Azure, GCP, and I can use Hugging Face Transformers in my code base to interact with those large language models without much effort. Nope. There we go. Looking at the runtime in Kubernetes, it's a bit more complex because obviously it's not managed, but you can run it on your own. But Kubernetes is an ideal place to do that because it has the ability to create bespoke runtime configurations for your large language models, and they need that. They can't run on any hardware. They need specifically GPU-optimized instances. And you can, in Kubernetes, run your large language model in a closed, secure environment. In addition, there's been a lot of work to facilitate runtimes in Kubernetes, specifically Microsoft released Kaito, which provides a Kubernetes operator for large language models. It makes it much easier to run LLMs in Kubernetes as well. So that was mostly everything that has to do with deployment. It is not as scary as it used to be, like a couple of months ago, even like 6 or 7 months ago. Running LLMs was much harder, so that's also about indicative of how, let's say, innovative the whole stuff is in that space. And now I specifically want to have a look at LLMs and their impact. So the great thing about about LLMs is that it also does one thing. It democratizes machine learning. Until now, when we did machine learning, specifically, you had to have data engineers and data scientists train models specifically with your data to create a predictive model. Large language models are pre-trained and pluggable, so you can actually make models available to, let's say, a non-data engineering crowd. It makes it much easier and accessible to allow normal software developers to interact with large language models. And the complexity of interaction is reduced to the prompt engineering, so the ability to actually tell the model that what you want to do. That comes with a price. Large language models have some issues. The one most most famous one is hallucination, right? When you just tell the large language model, it gives you an answer that sounds right, but it's completely made up and it's completely fake. And why is that? Well, large language models have no capabilities of reasoning. The only thing that they do is to give you the answer that's most likely to be right. That's predicting an answer that sounds right. It's basically your built-in machine management consultant, if you want one. It takes one to know one, right? So you need to reduce that problem. Data sets is another issue. They internalize their answers. So basically, using a large language model means that you're basically baking in a 2021 Google because that's when they were trained. Privacy is another problem. Internal data can be leaked by just asking the large language model. So there's a way to solve that, and it's an architectural pattern called retrieval augmented generation. Fancy word for a very simple principle. You detach the data for the answers from the large language model, and you reduce, or you basically confine the large language model to providing the mechanism answering the question, and you instruct the large language model to look for the answer somewhere else. And that somewhere else is a vectorized data source. Right? You basically say the answer for the answers you'll find in this database, right? And it's externalized from the model, and it's chunked there, and using an embedding model that basically does the whole chunking and storing. So when you use RAG, the large language model gets the question and it says, please look for the answer in this store, and it will look in that store and provide the answer with its own mechanism. So it's a combination of, and a separation of concerns, right? Store for the data is in this place, and large language model provides the answer there. And that basically gives a more specific answer to specific questions and the ability also to update things, update answers on the fly, right? And the reason why we do that is, or let's say the store needs to be a vector because that's the store, the most like the native store or the native format for large language models. And we use the vector format to allow that fast retrieval access from large language models. When we think of vector databases, most people would probably groan inwardly and say, okay, well, we've got NoSQL databases, document databases, key value stores, relational databases, vector databases, oh God, graph databases. That sounds like a lot, but it is also often sufficient just to use a vector support in your existing data store. You do not have to introduce a new vector or a new database type in your infrastructure. For most cases, the data sets are relatively small, and we can use an existing store with vector support. So the advantages here is that you separate the relevant input from the model, and you do not need to train a model extra for the purpose that you have, right? That also greatly reduces the risk of hallucination because the model has instructed to look for the answer in a curated and safe data set and doesn't have to come up with something from its own model. And operating costs are significantly smaller because you do not have to train the model, and you can also use a much smaller model to do that because you only need the ability to reason and about the answer and not provide a very clever answer from its own data set. So the use cases for AG is specifically in legal tech, for instance, a big one. Like if you think of the job of the paralegal to look at a specific case and find similar precedent cases in the library, often involving using books, right? That's a very tedious and costly, time-consuming job. RAG can simplify that significantly by using the retrieval ability and the ability to classify and match documents. Expert systems, same thing. If you think of, let's say, complex manual-based industrial cases where people have to also do lookups on thousands of pages of documentation, you can use a large language model in combination with a vector store to specifically ask questions and say, okay, where can I find part X, Y, Z for this engine or whatever? And specifically also matching systems because it's very, very good at semantically linking documents in enterprise data sets. For instance, policy data documents, for instance, like insurances, healthcare is another area where this is an excellent use case. So thank you very much, and I hope you enjoyed this talk.